Now let's think about the forces on long straight wires in magnetic fields. So the first thing to recognize is that the directions are going to matter. What is the direction of the current flow? What is the direction of the magnetic field? So again, the equation that's going to give us this is a cross product. And technically we're going to call it the L vector, or you can think of this as the I vector. So whatever this vector is, it needs to be the magnitude given by the length of the wire multiplied by the magnitude of the current, and it needs to go in the direction of the wire and of the current. And the reason it's usually shown this way is that this is actually already a simplification of a more complicated form. So if your current and magnetic field are parallel, such as the first situation shows, then your force is zero. Why? Well, think about your current just being made up of little charged particles. In this case, all of your charged particles are traveling parallel to your magnetic field, and we know that in fact, you don't have a force then. Otherwise, use the right-hand rule. So we can luckily just think about this as a positive charge that is traveling in this direction, right? For thinking about the current. And so if you do that, your magnetic field is into the page. So V cross B gives you a force to the left. So this wire experiences a force to the left. So always make sure you think about this. If your current was going the other way, then your force would be going in the opposite direction. A different orientation of the magnetic field gives you a different direction of your force. So always remember that what we're really talking about here is a force due to all of those little charged particles moving in our current. Now, we can always just use that the magnitude is given by I times L times B, where L is the length of your wire. As long as your wire is straight, your field is uniform, and your magnetic field vector is perpendicular to your current vector, or if you prefer to think about it, your length vector. Now, otherwise, not only would we have to think about the angle, but we would actually need to integrate, right? Imagine a situation where you have a uniform field, right? So if we have an area of a uniform field, but our wire is doing something weird, well, obviously your current is going to point in different directions in different places. So that means your force is going to vary in magnitude and direction. So that's why we think about it being a straight wire in a uniform field. If your field is varying such that it was stronger in one place than another, then even if your wire was straight, you would have to think about that changing. So normally we're going to deal with a simple situation where our wire is straight and the field is uniform, because otherwise you need to integrate. So please keep that in mind. So there's a simple observation that this the previous section actually starts with, and I'm just bringing it up here because this is again something that people figured out a while ago when they were first trying to understand these crazy magnetic field things. If we have two wires with a current between them, we would see that these wires actually attract. And this would have to be a really big current to actually observe this difference, or at least observe it without special tools. If we put opposite currents through, meaning one's to the left and one's to the right, these wires actually repel. So this would be an observation that you could make, and literally that you could make if you were careful enough in trying to make this observation. So these are forces that are much bigger than, say, the gravitational forces between these objects, but we need to try to understand where they're coming from. Now, the first thing you should try to think about here is that we know that a wire creates a magnetic field. And we just said that a wire actually experiences a force when it's in a magnetic field. So that's going to be how we can explain this. So in the situation where they're the same direction, think about how we're actually going to get that magnetic field. Now there's something really important about this picture. The magnetic field around the wire is created by the other wire, right? So if we think about this current and you use the right-hand rule, you know that above this wire, it's coming out of the page, right? So this wire is actually creating that field. If we think about this wire, below that wire, the field is going into the page. So that current is actually creating this field. So this is kind of tricky to understand about the picture. The wire on top is actually creating the field that is shown below. But of course, if we wanted to, this is also creating, right, a field up there, but we don't actually care because this field doesn't act on wire 2. So this is a little bit confusing, but note that basically this field is actually associated with that wire. It's creating it, and then this field is exerting a force on that wire. So the same thing is happening over here. So again, this current is creating this field where this current is creating this field. Okay? So use your right-hand rule to convince yourself that, again, this green field into the page is what you would expect below the wire on the top, and the blue field out of the page is what you expect from the wire on the bottom. Then you use the right-hand rule to think about the blue field interacting with the green current, and you do V cross B. So I cross B gives you a force down. Then we come down here and we say I cross B, where it's now in, gives you a force up. So in this case, you have an attractive force. Over here, when you do the same thing, you actually are going to get opposite direction. Notice that because here you have the same direction of field, but you have opposite current. So V cross B on top, now you have a force up. V cross B on the bottom, you have a force down. So take some time with this and really think through this. Again, what's confusing is that the field shown near a wire is actually the field created by the other wire. And that's how you can get to these directions. Remember that the magnetic field created by a wire does not exert a force on itself, right? I can't push myself, but I can push another person. Notice how these are labeled. These are a Newton's third law pair, right? 2 on 1, 1 on 2. These are Newton's third law pairs. So that tells you that these must be equal and opposite. Equal in magnitude, opposite in direction. So quantitatively, what do we get? Well, again, in this case, we're going to have perpendicular magnetic field to current, so we don't have to think about that angle in the cross product. It's just ILB, where L is the length of the wire. And we can actually think about the force on one wire or the other one. So the magnetic field created by wire 2 and current 1, or current 2, and the magnetic field created by current 1. And again, keep in mind, for all of this to make sense, this current is creating this field, and this current, oops, my color didn't switch. This current is creating this field. So we know that these must be equal because these are a Newton's third law pair. And mathematically, when you actually say, well, what is the magnetic field from one wire at the location of the other? Remember that the magnetic field created by a wire is not uniform. You must think about the spacing between them. And actually, if you look, it's going to be one current times the other, and the rest of this would be the same. So really, the force doesn't depend on which wire you're looking at, which does make sense. Now, there are a bunch of simplifications that go into this. One is that the wires need to be parallel, i.e. distance needs to be the same everywhere. Second is that these need to be fairly long. Why? Well, we're basically saying that the magnetic field is constant in the horizontal direction, and if you're at the end of the wire, weird things happen. So they don't need to be infinitely long, but they need to be pretty long, such that the amount that the magnetic field is varying over the length doesn't really matter. And again, they can't literally be infinitely long since the length does factor in. They need to be equal lengths, And again, if one was much longer than the other, then we would have to ask, well, what is the magnetic field happening over here? And then it's not uniform. So that's why they're equal lengths, L. And of course, this is a situation where there's no other fields. So all of the other fields are negligible, or it's an isolated system and we don't have to worry about anything else. Of course, if you had other fields, you can always do this with superposition. That will still work here.